Hey everyone, in this video we're going to be looking at multiple linear regression. So broadly we're going to be looking at the multiple linear regression model itself, how we can interpret estimates that we get using R, how we can calculate predicted or estimated response values given a certain value for our predictor variables, how we can construct new predictor variables from current ones to use as additional predictors in our model, and then also how we can assess how well our model is doing in capturing patterns in our data and how well our predictors are explaining our response variable of interest. So multiple linear regression is a generalization of the simple linear regression model. It's an extension, essentially, where we now have k explanatory or predictor variables, which we're using to model y, our response variable. So now instead of just x being our predictor variable, we have x1, x2, all the way up through xk, where we have k predictors in our model. So these predictor variables can be either quantitative or categorical, but we're going to focus on, just in this activity, quantitative variables for now as the predictors, but we'll talk about categorical variables at some point as well. So in this setting, the MLR model relies on an assumption of a linear relationship between each predictor, xj, and the response variable y. So some examples where we would use multiple linear regression, one that people often, it affects their lives when you're shopping for homes or selling your home, right, is modeling the selling price of a house. So when this is done, typically, this involves using characteristics such as the size in square feet, number of bedrooms, number of bathrooms we have, the year the house was built, maybe the particular neighborhood the home is in, or other factors like businesses that are close by, different things like that. So we can, it's a lot of information to absorb just as a single person if you try to look at many homes like this and try and think about like, okay, what should the price be? But we can actually use this, more formal algorithm using a large amount of historical data on the selling prices of other houses to estimate or predict what a certain house should sell for, given all the data that we have using multiple linear regression. Okay. Other examples that people use all the time, forecasting the sales of a company, right? Or the sales of a particular product. It's often of interest to predict this ahead of time to know how much product you need. You don't want to have too much of a particular product for your company so that you have a surplus, too much left over, you didn't sell it. But you also don't want to have too little to where you sell out of the product too quickly and lose out on potential money to be made. So maybe you'll model or forecast the total sales for a product based on the amount you spent in advertising for this product, how much the product costs, right? Probably as the product is more expensive in general, you would expect to sell less of it. Maybe you sold this product in a previous year, maybe it's like a seasonal thing, and so you can use previous sales numbers to try and forecast that. Or maybe you didn't, but you had a similar product that was previously sold, so that might be a good predictor to try and include in the model to help us explain or predict how much our new product will sell for, and then perhaps time of year. Okay. So in order to forecast something like this, it would likely be best if you had previously sold this product and you have data about the results for how that went, and now we're selling it again. But if you didn't, we could still use multiple linear regression to obtain some reasonable estimates or predictions. Another example, maybe a company is concerned about equal pay among its employees or paying its employees fairly. So they want to model employee salaries using factors such as the education level of the employee, the number of years experience in the job title, and gender. So this is an interesting case because you can use regression. Sometimes you're interested most in the response variable and just estimating or predicting that, as with the house selling prices example, or the forecasting the sales of a product example. In those cases, it's likely the interest is primarily on the response variable. Sometimes you're interested in a predictor variable more so than others. So maybe a company is concerned that gender influences or the pay of an employee differs by gender after controlling for the education level, years of experience, job title, and other factors of an employee. And so they could use a linear regression model where they predict salary of an employee using these other factors. And maybe if they find in the model that gender was a significant predictor, that might indicate a discrepancy in the fairness of pay. And so that is something they would look into potentially. So in that case, it's sort of like, actually, we're interested in a predictor variable's relationship with the response. And that might be the primary goal of interest in doing this type of study. Okay, so sometimes it's not all about the response. You can use multiple linear regression to explore predictors. Another one where maybe it's, again, more focused on the response variable. We could have a model predicting what a person's blood pressure would be, or what we would expect someone's blood pressure to be using information such as their age, gender, and their height. Okay, so this is very likely the doctor. When you go to the doctor, right, like they typically have some type of chart where they look up like, oh, a range of values that they would expect your blood pressure to fall in, right? So they use something, they might even use linear regression or something very similar, certainly, to take into account characteristics like your age, gender, and height. And then they get what they would expect for your blood pressure with some variation around that, but that's how they can, get an estimated value of that using data on many other people and what other people's blood pressures typically fall into. We can see if something potentially should be investigated further. Maybe if your blood pressure is significantly further than what this model would expect, it might be a red flag for something else going on. Okay. So let's think about in each of these scenarios, what are our predictor variable and our response variable for each of them? Okay. So maybe you could pause the video and try on your own and then see how you do comparing to what we get here, or you can just follow along as well. That works too. All right, so let's see. So we've got example 1 is on the housing prices. Okay. So in that case, it's actually predictors now, it's plural. So in that case, with the housing prices, our quantitative response variable is the selling price of houses, right? Okay. And we'll just put in parentheses like quantitative. And then what are our predictors in this case? So we've got size in square feet, number of bedrooms, number of bathrooms, year the house was built. And it said other factors. So we'll ignore the other factors here. So size in square feet, number of bedrooms, number of bathrooms. and the year each house was built are all quantitative variables. If you only had data on like 2 years of homes being built, you could treat that as like a categorical variable where you have 2 categories. But if you had many years of homes being built, like let's say you had homes from 30 different years in your data set, it's better to treat it as a quantitative variable. And we'll talk about the reasoning why more in a later activity where we talk about categorical predictors more. But here we'll just say, we'll assume we have data on many years, many different years. So we're going to treat that as a quantitative variable. Next example, so forecasting total sales. So that's our response variable, the total sales, right? Also quantitative. And our predictor variables in this case are all of these. Okay. So advertising expenses, the price of the product, the previous sales numbers for that product and similar products. And so we'll say and the time of year. So maybe it's like season of the year. For example, summer, winter, spring, fall. Then it would be categorical, okay, for the time of year. If it's referring to the date, that would take a little bit more careful consideration about how to include that as a predictor. But here we'll just assume we're referring to the season of the year, in which case it would be a categorical predictor. And let's see, if we were looking at the employee salaries, okay, so employee salary would be the response, right? Which is quantitative. And the predictors in that case are education level, years of experience, job title, and gender. So education level would be categorical. Maybe like high school degree, bachelor's degree, master's degree, so on. Years of experience would be quantitative, right? The number of years of experience. Job title, that would certainly be categorical. And gender would be categorical. Okay, so a lot of categorical variables in this scenario. And that's okay. You can have categorical predictors in a regression model, but the response variable for a multiple linear regression model must always be quantitative. And in this last example, we are predicting the blood pressure of a person, which again, the response is always quantitative, and the patient's age, gender, and height. Okay, so for age, someone's age in years, although that's typically reported as a whole number, it's quantitative and continuous. Gender is categorical and height is quantitative. All right. So that's all the response and predictor variables for each of those scenarios above here. And yeah, now we're getting into this a little bit more. We see some categorical variables, but the response variable is always quantitative. So a formal theoretical statement of the multiple linear regression model, we write as this, where we have y, our response variable, is equal to a linear combination of our predictor variables. So we have some number, some constant number plus predictor 1 times a different constant plus predictor 2 times its own slope or constant, and so on. And then lastly, plus a residual or error term. Okay. So this is the relationship that we assume is true between all the x's and the y variable here. But we don't actually observe these true regression values, the intercept and each of the slopes. Okay, we have to estimate these betas based on a sample of data to describe this relationship between the x's and the y's, or at least our best guess of this relationship. Okay. And so when we use a sample of data, we can get estimates for the betas, which we then denote with hats to say like, hey, that's our numerical estimate of the betas, but it's not the true value. It might be different if we got a different sample of data slightly. And then in the estimated model, it's important that note that we drop the residual term, the epsilon term here, and then we have a hat on the y because this is now our predicted response value, whereas just plain old y is the observed response variable value. Okay. So when we give the estimated regression equation, we actually will have numbers from software, from R, in this case, the programming language. We'll have numerical estimates for these betas that we then plug into this equation. Okay. But y hat's always just y hat, and the x's still just stay as x. So just like simple linear regression, we need a few conditions or assumptions to be met in order to conduct valid inference related to the model. So prediction intervals, other confidence intervals, or to use p-values effectively, and also to have reliable estimates, estimates of the betas that we can interpret in context. In order for those to be reliable, those interpretations, we need these assumptions to be true. So in general, these assumptions are all pretty much the same as for simple linear regression, but modified slightly. So before, for simple linear regression, we needed a random sample, so that's the same as before. And we needed a linear relationship between x and y. Now we need a linear relationship between each predictor, each x and y, holding all other predictors constant. Okay. This is phrasing that shows up that's important to include when describing the relationship between each predictor and y, each x and y. But it's important to include. We can only interpret the relationships now of each x with y if we say holding all other x's constant. Okay. Constant variance, so that's the same as before. We need our residuals to be homoscedastic. We need the residuals to be bell-shaped or normally distributed. We need the errors or the residuals to be independent of our fitted values, of our predicted values. Okay, so these assumptions are pretty much the same as for simple linear regression, the first 5. A new one for multiple linear regression is that we need no multicollinearity to be present. So in other words, we need that our predictor variables are not highly correlated with one another. This doesn't necessarily make predicted values worse, but what it does is it will make the individual regression estimates unstable or unreliable on their own. So typically we can interpret what these values mean in context if model assumptions are met. They have interpretable real life meanings. But if these assumptions are violated, especially multicollinearity, then these estimates can show or indicate things that are nonsensical or inaccurate. But to emphasize again, overall collectively, the y-hats that we get from a model would still be reasonable. Okay. So we check assumptions 1 through 5 the same as we did for our simple linear regression. But now we also have this multicollinearity assumption we need to check. And the most common way this is checked is using what's called the variance inflation factor. It's a measure of how correlated the predictor variables are with each other. It's actually based on the R squared. And you could look up the formula for it on Wikipedia, actually, but we won't get into the formula here. We'll just say it's a number that you get for each predictor. And the bigger the number is, the more concerning multicollinearity is for that predictor. Okay. And again, just keeping things simple as a rule of thumb, we'll just say a predictor has multicollinearity issues if its VIF value is bigger than 5. Okay. All right. And VIF values are non-negative, so they have to be 0 or bigger. So also talking about how we can interpret the regression model estimates now for multiple linear regression. Again, very similar to simple linear regression, but we have to be a little bit careful with the phrasing. So now for each of the estimated slopes, here's a general blueprint interpretation. And note that the first part of it, okay, when we just had simple linear regression, this is exactly the same as before, actually, the highlighted portion here. What's different is this additional phrasing that we have to say, holding all other predictors constant, or holding all other x's constant. Okay. We can, again, only describe the relationship between xj and y if we condition on all the other x's besides xj being held constant. If you allow other things to change simultaneously, it gets too complicated to be able to interpret in a single sentence like this. Okay. So that's why we do this, just for interpretability. The slope, the estimated slope, again, similar to simple linear regression, but a little different now. It's instead of just the expected value of y given that x is 0, now it's the expected value of y given that all the x's are equal to 0. Okay. So pretty similar. And again, want to emphasize these interpretations are only valid if these assumptions are met, all of them, especially multicollinearity. All right, so we've talked about it from a very general level here, but let's get into some real data to look at how we can use multiple linear regression. So we're going to be looking at a data set that hits close to home here. So it's on the Great Lakes. It was collected by the Great Lakes Observing Systems network of buoys that they collect data from. So for those not familiar, it's a little bit small in this picture here, but here's a picture of one of the buoys where they collect lots of measurements on the Great Lakes. So they measure conditions about the air temperature, water temperature, the wind speed, wave heights, all kinds of things. And this data in particular is just from 2 days because there's many buoys in the network. One on September 22nd, 2021 and November 9th, 2021. Okay, so there's all these variables in this data set. The time of the measurement, water temp, wind speed, direction of the wind. Okay. So here's a randomly selected 5 rows from the data set just to show you what it looks like. Okay, so there's the date the buoy measurement was collected. We have the wind speed in knots. which is a different unit of measurement than miles per hour, but same idea that the higher the value, the windier it was. We have the direction of the wind. These buoys are owned by different companies, but they all allow their data to be collected by this Great Lakes buoy system, which is cool. Okay. And then they're all across all the Great Lakes. So like this top one was a measurement taken by Cleveland and Lake Erie. This one in Munising, in Lake Michigan, okay, Lake Ontario, Lake Michigan, Lake Erie. So all over the Great Lakes, right? And so let's start by looking at a couple scatter plots. Okay. We're going to be focusing on modeling the wave heights. Okay. So here, yeah, here's the wave height in feet, which they described as like the peak wave height, like the tallest wave that the buoy had measured recently. Okay. Gets as high as like 6 feet here. And it looks like, it was quite windy. And then the waves were really tall there and as low as like 0.3 feet. So, and they're, the least windy. Okay, so we can already see maybe there's a relationship between the wind speed, just sort of eyeballing some of the data here, the wind speed and the wave heights, right? And if we plot the data, there's some noise, but there certainly seems to be a positive linear relationship between the two. As it's windier, the wave heights are taller. Okay. Maybe not the most significant finding in the world. Like, yes, when it's windier, it's wavier, right? But this might be useful because maybe we don't have a buoy out there. It might be more difficult to measure how tall the wave heights are, but maybe we can measure the wind speed really well in certain spots. And so we can estimate using our model maybe, or predict what the actual wave heights are, okay, for like safety for the pier or something like that. Okay. So multiple linear regression, this would be alone a decent, simple linear regression model. Now that we have multiple linear regression, we can take into account more than one predictor. So we can use more than just wind speed. Now we can also say, let's look at the relationship between the water temperature and the wave heights as well. So this relationship, not as strong, right? The wave heights and the wind speed understandably had a stronger relationship. Here it's not as clear, but we'll let the data tell us what's going on here, I suppose. Okay. So here looking at the table of pairwise correlations, which again, so like a table of numbers like this, we call a matrix. And if we want to look at the unique correlations here in the data set, we can just look at the lower triangular part of the matrix, because if you flip it over the diagonal, you actually get the same values in the top here. Okay. So here, for example, is the correlation. Here we have the correlation between the wind speeds and the water temperature, and that's 0.41. Correlation between the wave heights and the water temperature, 0.21, and the correlation between the wave heights and the wind speeds. Okay, so that's the strongest, right? We have a correlation of 0.7 between wind speed and wave heights. Then below that, so there's our table of correlations, gives us an idea of relationships that we see. Okay, and we saw that it was positive wave height and wind speed relationship that showed up in the scatter plot as well. Okay. We also have some summary statistics here. So again, this is about the wave heights. Okay. So we can see stratified by lake. Okay, so here's how many measurements we have from each lake. We have the average wave height. So Lake Erie had the shortest waves on average, and Lake Huron had the tallest waves on average. See, like, what was the tallest wave measured? 7.4 feet. That's really tall. And then for the minimum, right, 0 or close to 0 for all the lakes. So this is data or summary statistics stratified for each Great Lake. And then here we also have it stratified by the two, because there was 2 different dates. And so we can see, oh, maybe there's a difference by the day of the measurement, right? And it looks like a little bit potentially, but we won't account for that here. Okay. So let's see, what can we say about the relationship between wind speed and knots and the observed wave heights? Okay, so there is a positive, somewhat linear relationship between, between the 2 variables. So we could tell that again because the talking about wind speed and wave heights, because the correlation between them was 0.7, positive 0.7, and because the scatter plot had this upward straight line trend mostly. Okay. So what about water temperature? Yeah, so for water temperature though, and we'll say based on the correlation between being 0.7 and that's what we'll say about that one. For water temperature though, there was a correlation of, it wasn't 0.7, it was okay, between temperature and wave heights. It was 0.21. Okay. So it was only 0.21. So there is a, we'll say a weak but positive relationship between the temperature, between the water temperature, Fahrenheit, and the observed wave heights. And I don't know if we could say this is linear. I wouldn't call it nonlinear, but there's just almost no relationship here. It's very weak. So we'll just keep it at this. Okay. So yeah, let's get a statement of our assumed model using the wave height in feet is our response variable, and the surface temperature of the water and the wind speed as our predictors. Okay, so let's copy the blueprint of the assumed model. I'll just paste this down here. And when we do this, all we want to do is update what y in each x is representing. Okay. So something like this, where we say like, y equals this. Okay, so we'll keep this part exactly the same for any problem, for any scenario. And then we just define what y and each of the x's are in that context. Okay, so where y is the wave heights in feet, and then, oh, I guess, okay, I guess this part is not exactly the same because we do need to update the number of predictors here. So here our predictors are x1 is the, well, let's see what r treated as, which one is 1, which one's 2. Okay, wind speed is 1. So let's say where x1 is the wind speed in knots. X2 is the water temperature in Fahrenheit. I think that's how you spell Fahrenheit. And epsilon is the independent, identically normally distributed error term. So then I guess, yeah, the important thing is that we have two predictors. So let's reflect that in the theoretical model up here. So, okay, so it is important to take that part out. Okay, so that now we have just x1 and x2. And if we had three predictors, we would need plus x3 times beta 3 as an additional term before the epsilon. Okay, but just a two predictor model here. So here's how we can give a theoretical or assumed model statement for this problem. This establishing what we're assuming when fitting this model. So let's take a look at some diagnostic plots to help us check if model assumptions are met or not for fitting this model, okay, that were obtained using R. So let's skip down because the next part's going to ask, indicate if each assumption is met or not. Okay, so let's copy the model assumptions list here so that we can check each of these for this problem. All right. Okay. Okay. So random sample. So these measurements were not all collected for separate buoys. And some buoys are closer to each other than others. So technically, this is violated. You know, we don't have like a random sample of all the buoys on the Great Lakes, or we don't have a random sample of like all the spots in the Great Lakes we're interested in, probably. So technically this is violated, but we'll proceed for the sake of the problem. You know, and truly this is a pretty good starting point. Like we had measurements from different buoys on each day. It's just that since we had data from 2 different days, there's repeated measurements on the same buoy. And so technically that violates this random sample assumption. So that would need to be accounted for. But we'll just proceed here, acting like we had separate measurements, all from completely different buoys. Okay, so for the linear relationship between each predictor and response, let's see. So Looking at the scatter plots. So that's where we'll look at the scatter plots again, which we already looked at. Okay, so wave height and wind speed. Yeah, linearity looks great. That looked fine. Water temperature and peak wave height. It's not that there's a nonlinear relationship. There just doesn't really seem to be a relationship. So that, like, not having a relationship doesn't violate this assumption here. I mean, I guess so. To give some examples of what would violate it, right? So if we had the scatter plot and it looked like, okay, let's say it's like, yeah, we have X and then we have Y. Okay, if our scatter plot looked like this, this is what would be concerning because it's there's a relationship, but it's very nonlinear. Okay. Or, you could have something else that's like this, and you have maybe a pattern like, something like this also would be like, no, that's very nonlinear, but there's a relationship. Okay. Those would violate the linearity assumption. Here, it's more just like, maybe there's a linear relationship and it's just really weak. It's not super clear what's going on. So, yeah, so this does not violate that linearity assumption here, I would not say. Okay. So we'll say like neither, or we'll say both scatter plots show a weak or moderately linear relationship. So this assumption is met. Okay. Constant variance. So for the constant variance assumption, which is formally called homoscedasticity, we're going to be looking at this residual by fitted value plot. Okay. And what we're looking for is we want a constant vertical spread as we go from left to right on the plot. Okay, so again, some examples of how this would look if it were violated. I'll draw like 2 examples here. Let's say, yeah, we had X, and then we have our Y. Okay, and so some examples of how, okay, and then we have our dotted line. We have our dotted line in the middle here, or actually it's not really X and Y here. It's like fitted values. Okay, it's more like that. And then this was R versus S, like R residual versus fitted value. Okay. Okay. And how this would look if this assumption were violated, some examples of this. The most common is if you see fanning, which fanning would look something like this. Okay. This is like an example of a fanning pattern because if you look at the vertical spread as you go left to right, it's like it's outward, it's getting bigger as you go left to right, right? So this violates this homoscedasticity assumption. Okay. What about if it were, you can also have this case where it's funneling. Okay, so maybe it's like a bigger spread to start, and then it's, something like this. This is, yeah, what we would call funneling, where the spread is getting smaller for bigger predicted values. Okay, and that unfortunately also violates the homoscedasticity assumption. Okay, those are the two most common ways this is violated. You could also have like a bow tie shape where it's like bigger on the outsides and smaller in the middle. That also would violate homoscedasticity. Okay, but the main idea is that we're looking for a constant vertical spread as we go left to right in the plot. Okay, so here, let's see what we've got. So yeah, it's a little big. It's like this big. It gets bigger in the middle, and it kind of stays the same. Okay, but there's actually this point up here, so it's almost like the vertical spread is like, yeah, if we tried to draw lines that box it in, you know, it's like pretty constant vertical spread as we go left to right. I'd say so. Okay. And it doesn't need to be perfect. Just, you know, there's no clear evidence of fanning or funneling. So we'll say, since there, so since there's this fairly constant vertical spread from left to right on the residual by predicted value plot, homoscedasticity assumption is met. Okay. So it's important. I want you to note like which plot you looked at, which diagnostic plot, and what you saw that indicated whether or not the assumption is met. Okay. So here we saw a fairly constant vertical spread. So for checking normality, the next assumption, we want to look at the QQ plot. Okay. And we want the QQ plot to have points that all pretty much fall along the diagonal dotted line here. Okay. It's okay to have some straying away on the ends a little bit, but not too much. Here, this looks pretty okay. I wouldn't say anything super concerning here. You know, these 2 points, I would say if we could exclude like this point and then these 2 data points, so observations 27, 91, and 17, it would be, you know, chef's kiss, good to go. It would look great. But this is, there's a little bit of questionable outliers here. But overall, we'll say nearly all the points fall really close to the diagonal line, with a couple exceptions that are not crazy far away. So we'll say it looks pretty good. This is real data, right? This is what happens when you have real data. You don't get like clear-cut answers like, oh, it looks perfect, or oh, it looks awful. Like usually real data is somewhere in between, which is why we're looking at it, because that's the part of practice here, I guess. Okay, so for normality, yeah, since nearly all the points on the QQ plot, so again, noting which plot we're looking at and what we see, fall closely to the dotted diagonal line, the normality assumption is met. Okay. Independent errors. So we want the residuals to be independent of the predicted values. Okay, so we'll look at the residual by fitted value plot. So what we're looking for here is that we want the predicted value, the fitted value, to not be informative of what the error or residual value is going to be. Okay. So showing some examples again where this is like violated. Okay, and then we have like fitted values. Okay. Maybe we have something like this, and yeah, we've got the straight line through the middle. Okay, so some examples where this would be violated is if you have something like this. Okay. This would be problematic because for smaller fitted values, the residuals are always or nearly always negative. But for bigger fitted values, the residuals are nearly always positive. Okay. And so since the fitted values tell us some information about the residual or error value, that's problematic. It violates that independent errors assumption. The errors or residuals need to be independent of the fitted values. And this is an example of like a linear or straight line relationship between the two. But you can also have non-linearity. Okay, so you could have something like this, something like this, where it's like an oscillating pattern. It's very non-linear, but because there's a relationship again between the fitted values and the residual values, okay, so this should actually maybe just say just like residuals. Since there's a predictable relationship between the fitted values and the residual values, this would violate that assumption of independent errors. Okay. So here, let's think about this. Do we see any predictability in the residual value using the fitted values? In other words, if we knew the fitted value for any point, do we have a good guess as to what its residual or error value is? Like, I would say no. So if we look, let's say like, oh, the fitted value is 2. What's our guess for what the residual value would be? Well, it's like somewhere in here. That's a pretty wide range, and it's nearly the same as what we'd guess for other points as well. And that's kind of the same no matter where you look. So independent errors looks good here. So we'll say since there is no predictable pattern in the residual by fitted value plot, the independent errors assumption is met. Okay. And then lastly, multicollinearity. Okay. So what we're going to do is, again, we're going to use what's called the variance inflation factor values. So every predictor in a multiple linear regression model has a corresponding variance inflation factor value, which we call VIF. And we just are going to consider a predictor to have issues with multicollinearity if its VIF value exceeds 5 as a rule of thumb that we're going to stick to. Lots of rules of thumb in statistics, unfortunately. So here we can see, here's our two predictors, wind speed and water temperature. They both have a VIF of about 1.3. So it is not bigger than 5. And note that anytime you have two predictors, because the VIF measures how much a predictor is related to all other predictors in the model, because of how that works, if you only have two predictors in a model, they will always have exactly the same VIF value. But that's not necessarily the case if you have 3 or more predictors in the model. But again, anytime you only have two predictors, it will always have the same VIF value. And here we're looking if it exceeds 5. That's not the case here. So since none of predictors have VIF values above 5, there are no issues with multi-collinearity. Okay, great. So pretty much everything is met. I mean, our random sample assumption was a little questionable, but we're just putting our heads in the sand about that for a little bit now and gonna move on with the problem. So let's see. So this is the regression output for modeling the wave heights and feet as our response variable using the surface temperature of the water and the wind speed and knots as our predictor variables. Okay. So it looks very similar to the structure of the output for the simple linear regression model. And now let's give a statement of our estimated regression equation. So let's copy the blueprint interpretation from up here. There we go. All right. And then let's color that blue. All right. So what we're going to do here, and we can actually take some of this from the assumed model. Yeah, we can take the definition of the x's and y. Although we have y hat now, so we'll be careful about that. So okay, so we'll say where y hat is the estimated or predicted wave height in feet. X1 is the wind speed in knots. X2 is the water temperature in Fahrenheit. Okay, so notice we only have the hat on the y, keep the x's as is. But now we need to put in our numerical estimates for each of the betas. Okay, so here for the estimated intercept, we get that here, intercept estimate. Okay. For beta hat 1, the x1 is the wind speed in knots. Okay, so this is our coefficient. So we want to make sure we get the right one. You know, x1 is wind speed, so we need to get the coefficient for wind speed. Okay. And x2 is actually negative, right? x2 is the water temperature. Okay, so we can, instead of saying plus, we'll say minus. And notice I'm only using one minus. Yep. Right, and then we only have 2 predictors, so we get rid of this last part here. Okay. So here's the statement of our estimated regression equation. Based on the data and the model fit, we have that the estimated wave height is equal to this linear function of the observed wind speed and the observed water temperature. Okay. Oh, we need to make sure we get rid of that extra negative. There we go. Only one negative. Okay. So now let's interpret these estimated slopes in context. Okay, so beta hat 1 is, let's copy the beta hat symbol. Okay, general interpretation. We're going to copy this. All right. And we'll say for every 1 unit increase in xj, we expect y to increase or decrease by this, holding all other predictors constant. Okay, so let's make it specific for this problem. So for every, and let's do the first one. Let's do x1. For every 1 knot, So the unit is not increase in wind speed. We expect the wave height in feet to, and then since this is positive, we want to say to increase by this number, slope we got from up here. And then we're talking about the units for the response variable here. So I guess we can get rid of it here so it doesn't sound funny. We can say by this many feet on average. It's important to say on average, holding all other predictors constant. And in this case, we only have one other predictor. So we, instead of saying that, we want to say holding the water temperature constant. Okay, so now let's check out our final interpretation of the first slope. For every 1 knot increase in wind speed, we expect the wave height to increase by this many feet on average, holding the water temperature constant. Okay. So the idea is that we can only interpret the effect of wind speed if we're assuming a constant temperature, say 70 degrees for the water. If the water temperature were somehow changing as the wind speed changed, things get wacky and we can't give as clear of an answer. Okay. All right, so that's how we can interpret the first slope. For the second slope, okay, which is negative, we say for every 1 degree Fahrenheit increase in temperature. So notice that we always say increase here, even if the slope is negative. We expect the wave height to and now instead of increase, it's decrease because the slope is negative. We expect the wave height to decrease by 0.001 feet on average, holding the, and now it's all other predictors. In this case, the other predictor is wind speed constant. All right, 1 degree Fahrenheit. Yeah, great. So that's how we can interpret each of the two slopes here. Now let's interpret the intercept. So for the intercept, here, let's get the blueprint interpretation. There we go. Oops, did I scroll past it? I scrolled past it. And I guess we don't have to make these italicized. All right, so the expected, so instead of y, we have wave height. The expected wave height given, and instead of all the predictors being 0, so we'd say given that there is no wind, wind speed equals 0 knots. And the water temperature is 0 degrees Fahrenheit. Wait a second. Is, and then what's our estimated intercept? This many feet. Okay. So we're saying we estimate or predict that the wave height, if there were no wind at all and the water was 0 degrees Fahrenheit, would be 0.1 feet about. Does that seem reasonable? Not really, right? So the wind certainly is okay. Like having a wind of 0 knots, sure. Just means there's no wind, but 0 degrees means the water for the Great Lakes, since they're not salty, it's going to be frozen, right? Rock solid. So there's no way there's any waves. So this is not sensible in this context, however, since at 0 degrees Fahrenheit, the water would be frozen. Maybe if it were Celsius, in that case, that's right at the freezing point. So maybe the lake is 32 without being frozen. That could be possible. But yeah, here at 0 degrees Fahrenheit, it's definitely going to be frozen. So it's good to note, like, this is not a sensible interpretation. Yeah. But what we can do is we can get a predicted value for a 70-degree day with no wind. Okay. So to do that, we'll use our estimated regression equation. Okay. Oops. So in that case, we have, okay, x1 is the wind speed, which in this case is 0. x2 is the temperature, which in this case is 70. So then we can use Google for what it was intended for. It's a calculator. Okay. And then we get that many. And then we want to add the units of measurement on there. Okay. So what is the estimated peak wave height? Again, important to include the units of measurement, 0.066 feet. Always good to double check your prediction and see if it seems sensible, right? In this case, we're saying it's like a beautiful day, 70 degrees, no wind at all. Should that be super wavy? No, not really, right? We would expect little to no waves. So this seems good. Always good to do a little bit of a sanity check like that. All right. So that's how we can get a predicted value from our multiple linear regression model. Okay. We only had 2 predictors here, but note that we maybe don't have to use both of them. Maybe one predictor gets the job done good enough. And if so, which one predictor is that? Okay, so often you have the situation where you have many predictors available, like much larger than 2. And so a decision needs to be made or should be made about which predictors should actually be included in the model. Because we'll talk about it a bit. Just because you have a variable measured does not mean you should necessarily include that predictor in the model. Okay. So for example, maybe you're predicting the scores of college basketball games, and you notice that, like, oh, all the teams who had orange jerseys won last year. So let's include information about whether or not a team had orange jerseys in the model as a predictor this year. Okay, that might be information you can have, and it might seem like it does well, but it doesn't mean that's necessarily something you should include, because maybe it'll do really well last year, but it won't do well as a predictor next year. Okay. Or maybe it did really well last year, but all the previous years that rule did not work. Okay. So we want to let the data inform us about which predictors should we include in the model and which maybe should we drop. Okay, and not include as predictors. There's many different ways to do this. we're going to focus on two of the most commonly used metrics that help us decide that, which are referred to as information criterion metrics. So these are two common metrics. Akiki's, I think I'm pronouncing that correctly, but I'm not sure. Akiki's information criterion, commonly just called AIC, and the Bayesian information criterion, commonly just called BIC. These both are numbers you get for a model, for a given model fit, that describe goodness of fit, or how well that model is fitting the data. Okay, and they're based on statistical theory. So these measures are useful because they reward models that do a good job fitting the data. Okay, so like this relationship, it's like, oh yeah, it's capturing that trend pretty well. They reward models that can explain the response variable quite well. But if you start including too many predictors in your model that are not really adding much, okay, they're just fitting noise, a random pattern in the data, but not actually helping that much, AIC and BIC will penalize for that based on their formula. Okay, so they reward model fit, but penalize for the number of predictors included. And they both function very similarly. When the sample size n is bigger than 7, BIC penalizes more for more predictors, so it favors smaller models slightly, whereas AIC penalizes less for when the number of observations is bigger than 7, which is nearly always. Hopefully you have more than that many observations. But in general, they give similar results. Okay. So let's look back up at our output up here. Okay. And, oh, actually, we're going to have to look down. So, okay, so I have to look down, but the table, let's see. Okay, so we're going to look down here. And what we're looking at is, let's see, what is our decision regarding the inclusion of wind speed as a predictor in our model? Okay. So wind speed, yeah, just wind speed included in our model. Okay, so we have output for 4 different models that were considered using wind speed as a predictor, wind speed and temperature as predictor, so the 2 predictor model. Okay. And then we have the AIC and BIC for each of these models. So this is a simple linear regression model with just wind speed, and this is a multiple linear regression model with wind speed and temperature. Okay, so these are 2 tables for 2 different models that were fit. And we can look at the AIC and BIC values to compare them. In general, we want a model with the lower AIC and the lower BIC values. Okay. So in this case, this suggests that having wind speed and temperature both in the model is better than just having wind speed, because the AIC and BIC values are lower for this one. Okay. So let's cite those values here. So since, let's see, here's the AIC and BIC values, wind speed and temperature. So I guess we'll kind of answer both these bullets at the same time. So since, so it's kind of like, what's their decision regarding the inclusion of wind speed and temperature as predictors in our model. Okay, so we'll say since the model with both wind speed and temperature had a smaller AIC and BIC than a model with only wind speed, we decide to keep both predictors in the model, in our model. Yes. Okay, and then the values, values, smaller AIC because it was like this, which was less than, and let's go grab what the two values were. So the AIC for the two predictor model was that, the BIC was this, which were both less than the corresponding AIC and BIC for the single predictor model. Okay. Right, so the AIC for the two predictor is this versus this for the single, and then the BIC, this. There we go. All right. So pretty much it comes down to, we want the model that has the lower AIC values and the lower BIC values. So here, since that's the model with both predictors, we'll keep both in the model. So we will keep both predictors in the model. Okay. And we saw a little preview when we were looking down here a little bit, but okay, so we decided that keeping both predictors, wind speed and temperature, in the model was better than just wind speed. But it may be the case, okay, actually, I think I look at it below here. It may be the case that wind speed is related to the wave heights in a nonlinear way. Maybe they have a quadratic relationship, like a curved relationship. In that case, multiple linear regression can handle this by using sort of a clever trick. So what we do is, for example, in this case with a single predictor, we can fit what's called a quadratic regression model by including a second predictor that's exactly equal to x squared. Okay, and how this looks in the data, so I think it's helpful to think about like how this actually looks in the data, is that you would have maybe something like this, where you have like the wave height, you have the wind speed in knots, and then what you literally do is you add wind speed in knots squared as a third variable. Okay. So then maybe you have like an observed wave height of 2, but a wind speed of 4 knots. Okay. Then the squared wind speed is 16 knots. Okay, because you just squared it. And then maybe you have an observed wave height at 0, wind speed of 1, and the squared value of this is 1. And maybe you have like a peak wave height of 4, 3, and then this would be 9, and so on. Okay. So this is the structure of the data. And then you can sort of act like, even though we know that this is a squared version of this variable, of this column, we just act like it's another predictor in our model for estimating or predicting the wave heights here. Okay. And so that's how we can fit a nonlinear relationship using multiple linear regression. And you could do this with higher order powers as well. In other words, you could have wind speed cubed and then wind speed to the fourth power. Okay. But you wouldn't want to include too many predictors. You would probably want to do something like use AIC or BIC to decide how many you should include if you're going to go down that route. Okay. Right. So that's the idea behind how we can incorporate or account for nonlinearity. When we're just fitting a single linear relationship here, we're assuming that the points follow this straight line pattern, okay, which maybe seems reasonable here. But with the quadratic regression model, what we're doing, okay, so in here we plot the quadratic or curved fit in R, is that we're assuming the points kind of follow this trend. Maybe it has like exponential growth here. Maybe this makes sense. Like maybe somehow as it gets windier, the waves get taller at a faster rate. Okay. That could be the case. Maybe that's what the data is telling us here. So how do we decide between these two models? Like, well, which one's better? Just the linear fit or the quadratic fit? Okay. So here's the result for the quadratic fit. And we get the AIC and BIC values for this model. Okay. So let's compare. Let's see, and actually we have the table of output down here. So we had wind speed, and then we just had wind speed squared. So here's just wind speed again, and then here's wind speed plus wind speed squared. Okay. So this one has lower AIC, this model, but the BIC, AIC and AIC, but the BIC is higher, which is not good for the squared model. So there's a little bit of a discrepancy here between AIC and BIC. So let's note that, which can happen. It's not common, but again, for real data, we're sort of getting into the, you don't always see clear-cut things based on the results. So the AIC value for the linear model using as a predictor is larger than the AIC value for the quadratic model with a wind speed. Let's see what it was for the quadratic model here. Oh, here it is. For just plain wind speed. So it was like, okay, I put the wrong numbers in the wrong spot. There we go. Okay, so the AIC value for the linear model is larger than the AIC value for the quadratic model. However, okay, let's talk about the BIC values. So however, the BIC values is smaller, suggesting that the linear model is preferred. Okay. Let's see what the BICs were. Okay, so we had like this 309 and then 308.54. Okay. So AIC and BIC disagree here, which is uncommon, although not extremely rare. It's not extremely rare. So, in this case, I would say consult. Like if I was doing this as a real world study, I would consult a domain expert, like someone who's very knowledgeable about the Great Lakes themselves and maybe has more experience with modeling wave heights. But if we're just going off the modeling numbers here, it is a bit of a toss up, but we will select the model with the lower BIC, the linear model. Okay. And I think it's also just a good rule of thumb that if it's close, the general rule of thumb as well in statistics and predictive modeling, if models are performing very similarly, the best idea is to go with the simpler model. In this case, that's the linear model. Okay. That's just sort of like a empirically, based on people's experience with predictive modeling, that's typically the better choice. Take the less complicated model if they seem like they're doing the same. Okay. So that's what we'll say here. Note that if we had picked the quadratic regression model as our final model, it's important to include not just x squared, but x1, the wind speeds not squared in the model as a predictor for interpretability. Otherwise, you lose interpretability of the coefficient estimates, the estimated slopes. But note that in terms of predictive performance, it's maybe possible that it's suggested just to only have the squared version of x as a predictor in the model. That's possible. And this gets more into like data science and predictive modeling versus statistics. I would say like a purist statistician would frown at this. Like they would say, you need to include both. A pure statistician, like a data scientist or someone in more just predictive modeling would say like, oh, if this one has the lower BIC for that model with just the squared term, go ahead, just keep that. Who cares about interpretability? So, it depends on the context. Are you looking for interpretability or just predictive power? Right. Because if you look at the models here, considering one with just wind speed squared, not including the regular term as well, so losing the interpretability, you're maybe actually able to lower your AIC and BIC versus the full quadratic model, just having a squared term. So these maybe suggest, if you're only after predictive performance, maybe this is the best bet. But again, it depends on if interpretability is important to you for that problem you're working on, or if you're just looking at getting accurate forecasts or accurate predictions. So the last thing we'll talk about is a little bit more about AIC and BIC and why those are important. Okay. So a very common mistake when getting into multiple linear regression, as I've mentioned before a bit, is to include too many predictors in one's model. Just because you have the data does not mean it should go in as a predictor. Okay. I like to use this example of a friend I had in undergrad when I was studying statistics and first learned about linear regression. Okay, so they used data to predict college basketball game scores, and they had all these statistics you could measure, like rebounds per game, points per game, assists per game, total number of players who played in the game, points per game. All these metrics you could use about a team. And then they used that to predict how much a team would win by. And they had like 50 predictors in the model, right? Their R squared was really high. So R squared represents the proportion of variability in Y that's explained by our model. So they had an R squared that was like close to 1. And they thought, oh, I can predict college basketball games perfectly. Like, look, my predictions for my data set were nearly all perfect. Okay, but the problem with that is that you can get predicted values for your own data set that are really good. But if you get new data, they might not fit it that well. And that's what my friend ran into, right? So they tried to predict college basketball games for the next season and then did really poorly. Like they did worse than just a coin flip, 50-50 guessing the result of each game. Yeah. And so why did that happen? It seemed like their model was really good. They had a really high R squared. So that was due to what's called overfitting, which is an easy concept to fall prey to in predictive modeling. So R squared, which is a common metric people use to assess how well their model is doing, describes the proportion of variability in Y explained by the model, which if you have two predictors, you can say explained by X1 and X2. But R squared always goes up as you add more predictors to the model. So if you're using that as a gauge for how well your predictive model is doing, it's going to lead you to include too many predictors in the model. Okay. So that's why we want to use something like AIC and BIC that penalize for including predictors that don't add very much into our model. That helps us to avoid overfitting. So here's like a depiction of, like I was talking about my friend adding way too many predictors, and they're like, all my predictions were perfect. Okay, this is what that looks like visually. So this is an example of, so we looked at how you could include like an X squared term, which allows you to get a curve for your model fit. This is an example of including like an X cubed, X to the 4th power, X to the 5th power. Okay, you could include a ton of powers of X. So you have many, many predictors of included in your model, and you end up with this really wiggly function for your predictions in green. And you can perfectly match the pattern in the data, right? So here, the residuals are actually all 0 because you hit the points exactly, and your model has an R squared of 1. Versus this predictive model is based on one predictor in a linear relationship between X and Y. Okay, that's just a straight line. So it has some residuals, it has some errors. The distance from the points to or the difference between the height of the line and the points. Okay. So which model is better? Well, if you get a new data point, right? Just looking at this, it seems unlikely that you could expect the points to keep following a pattern like this, right? I mean, looking at what was going on, it seems like if you got a new data point, it'd probably be something like that, right? And in that case, the errors for the new points would be really high for the green line, but the blue line's doing really well, okay, because the blue line's doing a good job of not overfitting. All right, so the idea is that overfitting will hurt us when we have new points that we want to make predictions for. In AIC and BIC, because they reward fitting the data well, but not including too many predictors, essentially not having too wiggly of a set of predictions sometimes, they will help us avoid overfitting. So the last thing we're looking at here is that we had all these different kinds of models we could consider. Wind speed and temperature as predictors, wind speed and wind speed squared, or just wind speed squared. Okay, we have all these potential models we could pick from. How do we know which one to use for predictions? Well, it's simple as looking at which one has the lowest AIC and BIC. Okay, so let's see. AIC says okay, the lowest one is this by far, wind speed and temperature. And then what does BIC say? Okay, similar story for BIC. So the two predictor model, so since the two predictor model has the lowest AIC and BIC values among all candidate models, we should select this as our final model to use for making predictions. Okay. So it's a nice decision rule. Look at the AIC and BIC. And these are very widely used. And what's nice about AIC and BIC is that you can use them to compare across many models. And we'll get to use them later on for other types of models as well. So just like usual, the R code to produce all the plots and statistics that we did in this activity is appended at the bottom of the activity. And that's it. So that was an introduction to multiple linear regression.